All right, we're going to go through the notes that we take down on Friday's class. This is the intro example that we'll do in class, and then there was a follow-up of a force table that we also did on Friday. So we have here a character named Mark the Shark, and Mark is a hammerhead shark, and he is dangling precariously above certain death with this fire below him. And it might be a little hard to see, so I'm going to highlight where the strings are. You have a string of tension coming here, and he has a string that pulls straight across over here. And with these two ropes, he's at rest. He's balanced. So we have this equilibrium situation take place, and we're trying to better understand how can something be in equilibrium if it doesn't have four forces just in opposite directions. This is a case where you'll have three forces that are balancing each other, because the one at an angle is kind of taking the place of an upward and over force. So what we're going to do is we're first going to represent this drawing, and we'll give you some known values of how much Mark the Shark weighs and what one of the strings is, and from that we should be able to solve for the missing amount of tension. If you could redraw this situation of Mark the Shark with the two ropes in your notes, we are then going to draw a free body diagram for Mark just off to the side. So we'll label this the free body diagram. And Mark the Shark has a force of gravity down that we'll call the force of G. He has a tension force straight to the right, we'll call force of tension. We have to have some way of talking about these tensions, so I'll just label this as tension 1, and this is tension 2. That way we're consistent with that. So this would be FT1. And then we have this third one kind of going up at this angle. Try to do your best to match that direction, and we'll call that FT2. So this would be the free body diagram. If that's all they asked you to draw, then that's all we would show. We wouldn't break that diagonal force up into components unless we're trying to solve something. And in order to do that, we would do it on a separate diagram. So we'll have the free body diagram represented there, and then underneath we'll actually get to the problem. The problem is, assume Mark weighs 20 newtons and FT1 is 5 newtons. How much force of tension is in FT2, and what angle off the horizontal is that string? So in these kind of tension problems, you have to be given some things in order to work your way and solve it. And for now, we're not going to get into like how we determine the force of gravity. We have separate labs for that, but we're giving you the values of what these forces are. So when you actually go to solve a problem, you don't do your work up on the original free body diagram. So this up here, this free body diagram, we would like leave as the answer to draw the free body diagram. Down below, though, we can redraw that so that we can do some of the work on that image. So I'm going to redraw my force of gravity down, and since I actually know it, I'm going to label it as 20 newtons. I have this tension force 1 that's straight to the right of 5 newtons. And then I got this diagonal force. Again, we're not really sure how much, but that's the whole point of this and what we're going to solve. when we think about that diagonal force, it's really composed of horizontal and vertical parts. And if we label this as FT2, then we can represent these horizontal and vertical vectors that take the place of what FT2 pulling diagonally is really doing. To label those, we'll call it FT2 in the X direction and FT2 in the Y direction. Those would be the X and Y components of that particular diagonal force. Now, I very well could have drawn this vertically and then horizontally like that. It's just kind of, you break the vectors in whichever direction you want as long as you're consistent with it. The only reason I chose to do it out here is ultimately it's asking us what is the angle off of the horizontal. And so I would rather have the sides of the triangle referenced over here so that I can solve for that angle a little bit easier. If I were to break it up this way and that way, I'm going to have to do some more trig to figure out where that angle would be off the horizontal. So I have this right triangle. Some people like to redraw just the right triangle to work on it, but I think this is sufficient for what we're trying to do. And what we're going to be doing is writing net force equations. So the net force equations become your solution to problems like this. And it might be obvious as far as how big these components need to be in order to make it in equilibrium. But in future problems, it's not as obvious. And so I want you to get in the habit of always doing it a certain way so that you can get to the solution no matter what kind of situation they set up. So we write the net force in the X direction. There's a little sigma sign. And all we do is we just focus on every horizontal force that is listed, either a component or an actual force, and we're going to be adding those all up. Well, if we come up with a system of plus and minus, everything to the right is going to be plus, everything to the left is going to be minus. Then I can add all these vectors up, and they should equal out to a total. In this case, the fact that Mark's not accelerating anywhere, he's just hanging at rest, I know that the net force is going to have to add up to 0. So when I write that out, I'll say FT1, and you're just going to leave it as symbols. Don't fill in the numbers yet. Plus a negative FT2 in the X direction has to equal 0. That is a net force equation in the X direction. And then we'll do the same thing for the Y equation. All right, so up here I got this vertical component here, and I have this component here. Notice I'm not touching FT2 because it's not in the X or the Y direction. Vectors that don't align themselves to the XY plane, you don't ever see in these equations. So for this one, I'd have FT2 in the Y direction plus a negative force of gravity equals 0. So from this, I could plug in now. I have everything I need to solve for what these values of FT2 in the Y, FT2 in the X are. And by getting the components, that's going to lead me to, like, if I can solve for what this is and for what this is, that's going to lead me to what this is through Pythagorean theorem. So let's just go ahead and do that math. FT1 was 5 newtons plus, let's say we didn't, I mean, this is going to be pretty obvious, but if I add FT2 on the other side, that's going to equal 5 newtons as well. But let's just assume I didn't know what it is. FT2 in the X direction equals 0. And if I said, all right, go ahead and solve for what is FT2 in the X direction, I could just add on both sides FT2 in the X direction. And now all of a sudden I have that FT2 in the X direction is equal to 5 newtons. So this basically lets me solve for what that value is going to be. And by setting the math up like this, it just tells me like what the quantity is going to be. So from that, I know that this is 5 newtons. And you can kind of see the pattern here. The vertical, if I do the same thing, Ft2 in the y direction's unknown, but I got 20, whoops, let me back up here, plus a negative 20 newtons equals 0. Well, if I want to solve for Ft2 in the y, that's going to equal 20 newtons. So I have my actual values of how much over and how much up that diagonal vector takes. And now we just need to do a little bit of Pythagorean theorem to solve. So I'll just kind of give myself room over here. A squared plus b squared equals c squared. So if I take 5 squared, add it to 20 squared, that should equal the hypotenuse, or what is Ft2 squared. So let's see, I got 25 plus 400 equals Ft2 squared. And if I solve for what the square root of 425 is, you get that Ft2 equals 20.6. So that tells me how much tension is in that rope. I now know the value of this is 20.6 newtons. And now the last step is I need to find this angle. So I have 3 sides solved. You could do any trig function you'd like to solve this, sine, cosine, or tangent. As a little bit of advice, if I was more confident in these 2 numbers, like the 5 and the 20, because I got those straight off the problem, I might use tangent in that case, because tangent involves opposite and adjacent. Let's say I made a mistake with the hypotenuse. Instead of using that wrong number and then doing it again, this allows me to use the numbers that I'm sure of, and that I can at least get the angle part right. I just might miss points on how I solve this Pythagorean theorem. But if you're pretty confident in how you did that, it doesn't really matter which trig function you used. So last step, to figure out that angle, I'll say tangent of theta. I like to write out like what it is just in math language first, is equal to opposite over adjacent. So now I'll fill in what that means for my problem. Tangent of theta equals, and the opposite side of this angle, as a reminder, you start at the angle. Opposite is just whichever side of the right triangle is directly across from that. So adjacent is the one that is next to. And hypotenuse is always the longest. So if we just kind of remind ourselves of what the 3 sides are, this is going to be tangent of theta equals 20 over 5. So the tangent of theta is going to equal 4. Now, to solve that, I need to do an inverse trig function of inverse tan on both sides. So basically, tan negative 1 is the inverse of tan. That's going to get rid of tangent on that side, and I'll be left with theta equals. In my calculator, I have to write inverse tan of 4, and that gives me an angle of 70, let's just round it to 76 degrees. So this angle is 76 degrees off the horizontal. That gives me the values that I need in that problem. That's an example of what we would do with solving these kinds of problems. It's easy if there's just 3 forces and it's at equilibrium. What's going to happen later is there's going to be multiple forces acting on it and possibly be accelerating. And so these equations down here become much more important when the net force doesn't just equal 0, but it equals some quantity that we'd have to use more of to get to the value. So From here, we're going to move back to the lab and do a force table, and that will be a separate video to complete.